Students, this is the first set of notes in the Minerals unit, ES 4.1. What is a mineral? Just like the other sets of notes, for these notes you're going to be writing down the text that is in orange. If at any time you need a little more time, go ahead and pause the video, but also at the end there's a catch-all page with everything you needed to have written down. So we're moving from outer space down to Earth, looking at some geology. This photograph is in a quartz mine in Mexico with some really large quartz crystals. These crystals grow really large because the temperatures are warm. When temperatures are warm and crystals don't really cool off very fast, the crystals have more time to grow and they get bigger and bigger. So the title of the notes is ES 4.1, What is a Mineral? Go ahead and write that at the top of the page. And here we go. What is a mineral? Minerals are solid substances made from pure elements or compounds. Rocks are made up of combinations of one or more minerals, but rocks are not minerals. So suppose you found a solid substance on the ground. How would you determine if you were looking at a mineral or a rock? Minerals must have 5 characteristics, which are abbreviated as SINC, S-I-N-C-C. S is for solid, I is for inorganic, N is for naturally occurring, C is for chemical composition, and the next C is for crystal structure. Solids. Solid means it can't be a liquid or a gas at room temperature. Inorganic. Inorganic means not living nor derived from living things. N is for naturally occurring. That means it's made by the earth, not by people. The first C is for chemical composition. That means only certain atoms are present. And it can be written as a chemical formula, which means it's a pure substance. You see some examples below, like rubies have a chemical formula. 2 aluminum atoms and 3 oxygen atoms bonded together makes ruby. The second C is for crystal structure. That means the atoms arrange themselves in a recognizable geometric pattern. And there's some examples in this chart on the right side. Minerals can be pure elements, like gold or aluminum, or minerals can be compounds, which are made of 2 or more elements. One of the most abundant minerals on the planet is quartz, the chemical formula for which is SiO2. Gemstones are also minerals. Rubies are the red form of corundum, known as aluminum oxide. Al2O3, 2 aluminum atoms and 3 oxygen atoms bonded together. This is a picture of sand under a microscope. And different beaches have different kinds of sand. You get bits of all sorts of stuff in there, seashells and plastic and glass. But a lot of beaches, the reason why they have that kind of whitish, brownish color is because there's a lot of quartz in there, a lot of silicate minerals. So the difference between rocks and minerals is important to be able to distinguish. Minerals are a pure substance. Minerals can be elements or compounds, and rocks are made out of minerals. So some examples of minerals include minerals as elements like gold, aluminum, and sodium. or minerals as compounds, sodium silicate, calcium carbonate, or sodium chloride, which you know as table salt, uh, and it's also sometimes called halite. Why do minerals matter? Minerals have all kinds of uses from construction to electronics to medicine. Minerals are important to human health and well-being. We need calcium, potassium, sodium, and zinc in our diet, all of which are minerals. The Earth's crust is made up of elements. These elements make up minerals. The most abundant minerals in the crust are the silicates, which contain silicon and oxygen. Over 90% of Earth's crust is made up of silicate minerals. Common silicates are quartz and feldspar. So you can see in the pie chart here, oxygen is the most abundant element in Earth's crust. But when in terms of minerals, oxygen is not a solid at room temperature, so it's not really a mineral on its own. So the most abundant mineral is silicon and oxygen together, which is called a silicate mineral. How do minerals form? Minerals form under a variety of conditions, including the cooling of molten rock, the evaporation of liquids, and the cooling of supersaturated solutions. Often mineral formation involves high pressure and temperature. As that mineral forms, the atoms arrange themselves into recognizable patterns. The pattern of atoms gives the mineral its specific crystal shape. Temperature changes can occur quickly or slowly. When minerals cool slowly, which is happening at higher temperatures, the crystals get bigger, like we saw in that picture at the beginning. Here it is again. Quartz mine, Mexico, huge crystals. It's pretty warm down there. When minerals cool off quickly, which happens at lower temperatures, the crystals are smaller. So a little further explanation about defined chemical composition in minerals. That means that there are only certain atoms present. For example, quartz is SiO2. That's one silicon atom paired with two oxygen atoms. If different atoms were added to this compound, you would have a different compound and thus a different mineral. Every mineral can be assigned a unique chemical formula based on the elements it contains. In silicate minerals, which are the most abundant in Earth's crust, silicon and oxygen are often bonded to metals. For example, the mineral magnesium silicate, also known as pyroxene, is found as MgSO3. This formula contains a silicate anion, SiO3, bonded to a metal cation, magnesium. Further explanation on crystal shape in minerals. Every chemical compound, and thus every mineral, is made up of atoms bonded together. The arrangement of electrons for each element causes them to bond in particular ways. This is what causes the visible pattern of atoms, which is your crystal shape. Here's a picture of bismuth with a very interesting crystal shape. Depending on the elements, the bonds can be strong or the bonds can be weak. Weak bonds are broken more easily than strong bonds. When a mineral breaks along weak bonds in a particular place, it's called cleavage. For example, halite breaks into cubic shapes. You can always predict that if you break a piece of halite or table salt, it will be in a cubic shape. And if you look at salt under a microscope, which is what this picture is of, it's actually little cubes. Mica is another mineral, and it has flat cleavage. The flat cleavage pattern is due to weaker bonds between the flat layers. And so it comes apart in these sheets. And here's another look at some common crystal shapes, a few different minerals here: fluorite, wolfenite, tanzanite, azurite, amazonite, emerald, and rhodochrosite. Rhodochrosite? We've got isometric, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and trigonal. You don't have to memorize any of these fancy names for minerals or their crystal shapes. What you have to know is that the crystal shape exists and that each mineral has a particular crystal system. So that about wraps it up for the first set of notes on minerals. Here is the page with everything you were supposed to write down. You can pause it here and catch anything that you missed.